I'm Max. I'm going to be going over all of the solutions on the spring 2024 physics exam, physics 2 exam. One thing I will say before we get into it again, since this is multiple choice, I'm not going to be doing metric conversions. Anything that's like 10 to the power of whatever, you can just like look at the multiple choice answer and figure it out whether you're in the right ballpark, even if the magnitude's not right. So we're just going to be skipping that in the interest of time. All right. Let's start with number one. Point charges here as such, 1, 2, and 3, side length of distance of 5 centimeters. Charge 1 is -2, charge 2 is +2, charge 3 is +3. And what is the magnitude of the charge on this charge 3? Now, this is just a Coulomb's law question. We're just going to sum up all the charges here. So again, just this force equals K, both charges. Force, we're going to do it on the x direction first. So x is equal to, going to be this straight shot here between 2 and 3. Of course, multiply by k, which is 9. And divide by d squared, which is 5 squared. And then you also have this charge here. And we can actually subtract it here. So we have the 3 times the 2 again, times the 9, times the 5 squared, which looks familiar. The important thing is this is an equilateral triangle. This is going to be an angle of 60. And for the x, we want this part of the triangle, which is given to us by cosine of 60 degrees. So this will give us the magnitude in the x direction. So 2 times 3 times 9 divided by 5 squared minus 3 times 2 times 9 divided by 5 squared times cosine of 60, 1.08. And then we have the force in the y direction, which is just impacted by this here. It's this 3 times 2 times 9 divided by 5 squared. Here we want this component, which is the sine of 60 degrees. So again, 3 times 2 times 9 divided by 5 squared times sine of 60 degrees. You get 1.87 term. Now, if you square root both of them squared plus, this one squared plus this one squared, you get 2.16. Again, metric conversions, I never converted these, so this is correct. All right, number 2. We have 3 beads. So bead 1, bead 2, bead 3. So bead 1 has 8 charge, bead 3 has -1, the other one has 0. These two touch, so that means that each of them now have 4, and bead 3 still has -1. Then these two touch. The sum of their charges is 1.5, or sorry, 3. So if we divide them amongst the two charges, charges, we get 1.5 for each of them. And now we want the magnitude of the force between 2 and 3 if they are 10 centimeters apart. Very simple Coulomb's law question. 4 times 1.5 times 9 divided by 10 squared. I got 0.54, so 1 is obviously the correct answer. Okay, we have another one. A charge at the origin, x equals 0, of 1 microcoulomb, and another charge at x equals 9 of 4 microcoulombs. And we want a charge where the net force is 0. Always with these questions, check, can you shove it in the middle somewhere? Since the two charges here, they are 1 and 4, they are both this positive. That means that you can put something in the middle and they will both, I guess in this case, try to attract it, which will keep it stable. So we want, to put a -5 charge here somewhere, we don't know where. To figure out how, let's define this like x term. If that's the case, then we can just use Coulomb's law. And, you know, in the Coulomb's law, the k term will cancel and the q1, like the -5 term, will cancel. So effectively all we're saying is we want 1 over x to be equal to 1 over x squared to be equal to 4 over 9 minus x squared. Easiest way to solve that one, don't plug it into your calculator. Your calculator will do the work for you. 1 over x squared, 4 over 9 minus x squared. I got 3. The correct answer is 3. There you go. Uniform electric field shot from the origin. This is a kinematic one. What's the maximum y the electron reaches in meters? Okay, so we're given mass. Remember from physics 1 that force equals mass times acceleration. I feel like my handwriting got so much worse between the two videos I recorded here. We're also given that force is equal to charge times the electric field. So we're in a field here, right? And this is a field that points upwards, but an electron will always go against the electric field, which means that it's slowing down the upwards velocity of that electron, right? Which is initially 200. Now, what do we do with this information? So first thing is we want to find the time at which the velocity dies. So velocity is 0 at the time where, well, we start with 200 velocity, and we're decreasing by a acceleration times the time. What is our acceleration? Well, if we combine these two formulas, we can get that acceleration is equal to charge times electric field over mass. Charge of an electron, 1.6 times stuff I don't care about, times 0.5 divided by 9.1. I get 0.0879. If I take 200, I divide it by that, I will then get a time of 2275. I'm not sure if that's correct, but we'll see what happens. Okay, and at that point we can solve for the actual y here. So the y, it starts at the origin with 0. It's given a velocity of 200, so times t, and it's also given an, or I guess it's slowed down at a rate of our acceleration here, t squared over 2. Let me do the math here. Minus I got a very large number, 2.275 million. For the purposes of the question, 0.23 will work just fine. Integral problems, you always hate to see these, but you know there's going to be at least one here. Let's use this this formula here if we can, or this picture here if we can. So the magnitude of the electric field on the y-axis. We're going to have to do this formula here for the continuous electric field, where essentially the electric field is equal to k times the integral between two values, we'll say negative L and L here maybe, of dq over r squared. Q over r squared. Now I will also say, in this problem, we only want the y, position of whatever we're integrating, but we'll get cross that bridge when we get there. What is dq? Well, dq is a small segment of charge. We have a charge density here, lambda, and we know the entire wire is of length 2L, right? So if we were to just multiply a small strip, say we'll call it dx, by this charge density, so a small like strip times the amount of the density, right, charge per unit, we get the charge of that small strip. So that's how we can just convert to dx. However, one thing to note here is that the charge present here isn't 100% like what's being acted here. We want the magnitude of the electric field on the y-axis exclusively. So that means we actually have to multiply by, say this is lambda, by the sign here. The sign of theta. Now, you might say, oh my god, another variable theta, you know, how do I do that? This isn't too bad. The sign of theta will always just be, it'll always just be this y over this r here. So in the end, we transform this into k negative L to L times lambda over r squared times y over r. Notice, we're only integrating with respect to dx, which means that both lambda and y are constants and can be moved out front, hence what you see here. And all that r is square root x squared plus y squared. So if we're raising r to the third power, we're just raising x squared plus y squared to the 3/2 power, since they're on the denominator, negative 3/2. So this would be our answer, number 1. Okay, magnitude of the electric field here with these charges 1, negative 1, and 1. Super straightforward, just point charge electric field shenanigans. Let's multiply this all by k afterwards. We have a charge 1 here over 4 squared. For the x, let's do the x's first. And then here we have the a minus charge, right? Minus 1. What is r? Well, this is actually a, you know, funny triangle, Pythagorean triple. So r is 5. But we only want we only want the x component, which we get from taking the cosine, which is 4 over 5 here. So we multiply this times 4 over 5. And this is our x component. Y components, pretty similar, right? 1 over 3 here, just here, and this. 1 over 3 squared. This should also be squared. And then minus plus, I don't know what I did there. Plus minus 1 over 5 squared. Here we want the sign to get the y component, which is just going to be 3 over 5. And if we take each of those components, square them, add them, do whatever the heck, 9 over 4 squared minus 9 times 4 divided by 5 divided by 5. Could easily be doing the math wrong here. It's a little bit annoying. 9, I guess 1 minus 27 divided by 5 divided by 5 squared. Yeah, I got 0.83. So it's exactly correct. This should not lead you astray. Okay. Thin rings. Annoying question for sure here. Center is located at the middle, but we are given the formula for a charged ring. So if you have this formula, use it for sure. We want to find the positions on the z-axis for which the electric field is 0. So that means that the electric fields of the two should cancel each other out. Simply speaking, when you apply this formula, so QZ, we can just say like QZ over, what is that? It's KQZ over Z squared plus R squared, 3/2. Z squared, this is the small ring, so we're going to use R squared to the 3/2 power is going to be equal to K 8QZ over Z squared plus 3R squared to the 3/2 power. And when you solve this, I'm not terribly excited. Some stuff will cancel, you know, of course. But ultimately, you have to plug it into your calculator. This is a 1. Actually, I can do it right here. You don't even really need to plug it in, actually. Take everything to the 2/3 power. What that'll do is it'll go like this. 1 4 Z squared plus, you could probably just say 9R squared over Z squared plus R squared. You'd get 4Z squared plus 4R squared is equal to Z squared plus 9R squared. You can kind of see it coming together now. 3Z squared. Sorry, this probably should be over here for 30. 3Z squared is equal to 5R squared. You get this, plus or minus 5/3R. And obviously, if z equals 0, the ring is completely symmetrical, so the x cancels itself out, and there's nothing on the y. There's, you know, obviously there can't be a y component to the electric field there. Oh, okay. A sphere, a uniformly charged sphere of radius 1, is surrounded by a shell of radius 2. So not to scale, we have 1 and we have 2. If the net charge on the sphere is 2 and the net charge of the shell is 4, what is the electric field at a distance of 1.5 meters from the center of the sphere? 1.5 meters is like here. First thing, shell rules. Electric field inside of a shell is nothing, so the shell does not count. We are just concerned with this circle of radius r, which can just be effectively compressed into another point. So we have a distance of 1.5, and this is net charge on the sphere is 2. So we're just going to do 9 times 2 divided by 1.5 squared. I made a syntax error on my calculator, and I got 8. Boom. Easy as that. These ones. Okay. What is the magnitude of the electric field at point P? Well, okay, you can kind of imagine these charge densities like emanating from each of these. So like here you'd get a 5 coming this way and a 3 coming this way, and then, you know, from all the way over here you'd get a 1 coming this way. This is when we start getting into flux, by the way. And because of this, the flux is, what is this? Yada, yada, yada. Number 9. Am I the right one? Yes. We do not have work written down for this one. I think it's, okay. So the flux here, you can see that these all cancel, and we just essentially have 1 coming in this direction here. Now, we want the magnitude of the electric field here. Where is it? Magnitude of the electric field. And that is going to be essentially just proportional to this over this. Now for the infinite sheet, we just want to take that 1 divided by 2 divided by epsilon 0, 8.85, and we get 0.0565. So literally just this is the that sigma at that region is that like -1, just divided by 2 divided by 8.5. That'll give you what you need here. Yeah, that's all it is. Okay, this is an interesting question. So these three spheres have the same charge density, and we want to know how the magnitudes of the electric fields at point P compare. Now, these have the same charge density. The P is always the same difference away. So the intuition might tell you the larger the sphere, the bigger the volume, and thus the larger the total charge. And yeah, that's pretty much correct, with one note here. So the enclosed charge, if we're like drawing a Gaussian surface, it's only going to be as big as like the surface we can enclose. So like a circle that's like way bigger than this, it'll be the same as C. C is going to be greater than B because you have this like extra enclosed charge here, right? But ultimately, there is a stopping point. Just here, it's not applied. So yeah, there's more volume in C, so it's the greatest charge, greatest electric field than B and A. A and B surround a point charge. Let's go write it in 2 right here. The net charge on A, okay, this is a very simple problem. These are conductors, which means that this 2 inside induces a -2 on the A here on the edges. But A is a net charge of -1, which means that the other edge must now have a charge of -1. B then gets this -1 here, or sorry, it gets a +1 to counteract that -1, and that's just the answer. Okay, electric potential. The difference between electric potential and the electric field is that the electric potential has no direction, you just add stuff up. So let's label these. This is 5, this is -9, and this is 2. So here the electric potential, you can see it is mentioned as here, charge times voltage. Voltage doesn't make sense. What am I looking for? I'm looking for the wrong thing. Where's voltage? I don't know. Here, yes. It's just KQ over R. You add those all up. So it's super duper simple. You don't have to worry about anything crazy. K, let's go with Q1, boom, over R, 4. Add that up with, your -9s times 5. This one would be divided by 5 because the radius is larger. And then 2 times 9. Sorry, this is -9 times 9 for K, divided by 3. So hopefully that should all add up nicely. Times 5 divided by 4 minus 9 times 9 divided by 5 plus 2 times 9 divided by 3. 1.05, rounded down to 1.0. Electric field is that, whatever that is. Oh my god, it's getting late. Those are our numbers. What's the potential difference? This is your equation at hand. It's equal to, final is 2, initial is 1. Make sure it's negative here. It's equal to E times ds. So E ds. When we integrate this here, a plus bx, we're integrating over x with respect to x. So 3 plus 4x, when you integrate, it will become 3x plus 2x squared, or 4x squared over 2. And, you know, plug in 2 to this, you get 6 plus 8, or 14, and then minus, plugging in 1, you get 2, you get 5, and you end up with 9 here, but then, of course, there's the negative ahead of it, so negative 9 is your final answer. Number 14, electric field in the x direction at x equals 3. So there's one, this isn't on the formula sheet, but you can like derive it. This makes this question a whole lot easier. Again, you can derive it using like these formulas here, I believe, because you have like this, and then you can convert j into I, and then I into v or whatever. Yeah, essentially x equals 3. Rise over run is 2 over 3. Or actually, this whole thing's 12, so the 2 is actually like half of 12, which is 6. So you get a 2, which is then, you get a 2. Sorry, headers. Oh yeah, okay, and yeah. The easiest way to look at it is just through this equation here. Electric field, it's just negative derivative of voltage with respect to x. That's all it is. So you'll have a -2 scaling. Boom, there's your first answer. Okay, I like this question. Between points P and Q, I'll start at P. So here you have, we'll start at P. It splits off into the 2. So we have the 2 here, and then the 6 here, right? And then the 6 one goes through the 4 before it meets with the 2. So we have the 4 before it meets back together with the 2. So we have this diagram here. Here, the P splits into 2 and 6, just like it did last time. So we have 2 up here and 6 down here. At which point the 6 follows into the 4, just like it did last time, before it reconvenes with the 2 here. So same plot here. Here, what does it do? Well, it splits into the 2 and 6. And then the 2 then leads into the 4 before the 2 merge together. So here, the 6 is alone versus the 2 is being alone. So this one's different. It's case 3. Okay. These ones are kind of a lot of work, but yeah. Okay, let's redraw it. So we start with a capacitor 1. So it's 6. And then it splits off into 3 and 4. So it splits into 3, which is 4, and 4, which is 2. And then these merge back together, and then go into capacitor 2, which is 6, and then the circuit ends. So yeah, this is definitely my recommendation for how to draw these in just a way simpler fashion. It makes things a whole lot easier. Okay, so first things first, these two are in parallel, which means we can just add their charges, and we end up with a devilish 666 configuration here. These three are now in series, which means we can add them all up. Not add, but 1 over 6 plus 1 over 6 plus 1 over 6 is going to be our new capacitance, and it turns out to just be 2. Now, the battery is supplying 12 volts to the whole thing, which means that this lone capacitor would theoretically be getting 12 volts. Multiply the two together, just make sure I'm not doing this, or I am doing this correctly, and you get 24 coulombs, right? Because of this equation. Now, one thing that you have to know, but it's not on the formula sheet, is when they are in series like this, the voltage is split across the three, but the coulombs are the same. So each of these actually has 24 coulombs right now, which means that each of these has 4 volts. Likewise, when they are in parallel, the voltages are the same. So this has 4 volts and this has 4 volts, but the charges are split, and the charges get added up into what they are now. So this ends up being 16 coulombs, and this is 8, and you can see that together they make the 24. But yeah, this one, which originally was 3 or 4, 3, it has a 16 now, and so that's the correct answer. All right, equivalent capacitance, as is just another capacitor reduction. Let's start here. We can see that it branches into C1 and C3. C1, which is 2, and C3, which is 4. C2 follows with, or C1 follows with C2, which is another 2. Then they merge together into C4. That one's a pretty straightforward circuit by itself. So first thing we do, these two are in series. 1 over 2 plus 1 over 2 is 1. So we have a capacitor with 1 and a capacitor with 4, like so, and then a capacitor with 5. These two are in parallel, so we add them together. 5 and 5. And then we add them up, 1 over 5 plus 1 over 5. These are in series, so we put the reciprocal, and it ends up just being a resistor with 2.5, or a capacitor of 2.5. Okay, all right. Resistance R. The wire is stretched to become 3 times as long while maintaining its volume. Resistance, first off, let's move down here. Resistance is volume over, dude. It's volume over I, which, well, no, it's not. Sorry, that's not volume. Oh my god, I'm tired. That's voltage. It's rho proportional to length over area, right? Now, the wire stretches to become 3 times as long as the original wire while maintaining its volume, right? Volume is equal to the length times the area. If the volume is constant and the length becomes 3 times as long, then the area must become 3 times as short. So we get a 3 times increase here and a 1/3 increase here, which just leads to a 9 times increase overall. All right, number 19. Oh my god, almost there. So we want power dissipation in wire A. They both have an equal length. We have a 2 millimeter diameter, not a radius, because they couldn't have made it easier. A current flows through them, and power is discharged. So power here, I squared R, is probably the way we're going to go here. So power equals I squared R, because I is just given. And to note, they have the same material. So the total power, right, is going to be equal to just the sum of the two parts. So I squared resistance of B, and then I squared resistance of A. Now, the two I squareds, they don't matter. They're the same between the two. Another thing that doesn't matter, since they're the same material, this rho does not matter. The only thing that will effectively matter, so I'll go I squared rho, is this length over area term. They have the same length too, so I can put the length even out here. The difference is this here. So A is 2 millimeters, which means the radius is 1. So we have like a 1 pi, just a pi down here. Whereas with B, you have this, which is a radius of 0.5, which when squared, 0.25, right, pi. So you can factor out the pi or whatever. The important thing to note is the relationship between the two, right? One of them is 1, and then one of them is like 4. So B is 4 and A is 1. Right? So for every watt of power, 1 watt that A dissipates, B will dissipate 4. So if 6 are made total, then this will 1/5 times 6 is how much A will dissipate. It's 1.2. Okay, final question. We have a copper wire with a conductivity, with a cross-sectional area. What is the drift speed of electrons? This is just going to be this one here. So drift speed is equal to, what did it say? J over N, which is like the density times the electron, N, E. Do they give? Yeah, they give N here. That's what this is. Now we're not given J. What is J? Well, it's I over dA. So I over dA. So yeah, it's just I over A and E. Now we don't have I, but we have an area, and we have the conductivity. So we can convert I to the resistance here, as long as we have the volt differential, which we do. So let's do that. I equals V over R. So V over R A N E. Now we don't have R, but we do have length and area. So, well, we don't have, and we do have conductivity, not resistivity, which this is. So R is going to be equal to L over sigma A. So V sigma A over L A N E. A's cancel here, thankfully. And we get that it's equal to the voltage, 1 times the conductivity, 6 divided by the length, 2 divided by N, 8.5 divided by E, which is 1.6, I think. Formulas? 1.6. I got 0.22. Yes, and that's correct. Exam's done. Thank you.